In this video, we take a look into the firmware extraction via the bootloader. And this might be helpful if you cannot get access to a UART shell because it's password locked, or if the pin to poke method doesn't work. To understand what's happening next, let's have a quick look into the starting routine of an IoT device. If we boot up the device, the first stage bootloader gets executed. This is a small bootloader that comes from the chip manufacturer itself. It initializes some hardware before handing the control over to the second stage bootloader. The second stage bootloader is stored on the SPI flash, and the developer made the decision to use the famous Das U-Boot bootloader. Our device, of course, also has some RAM, and this is where the action takes place. The second stage bootloader, U-Boot, takes now the kernel and the root FS from the flash and loads it into the RAM. Afterwards, it starts executing it. This will boot up the device like this. The thing is, we do not want to start the device because then we get locked out. All we want to do is we want to access the firmware. Therefore, what we're going to do is loading the flash content into the RAM, but this time we are not executing it, we are printing it out with the memory display byte command. All we have to do is to store the output into a local file on our laptop like shown in the video before. So let's do this. Here we have now the setup, our bus pirate, the camera and a UART connection to it. If we power on this device and press any key, we can interrupt the bootloader, which brings us here. Unfortunately, this bootloader is password protected. We can reverse the password, but only if we have access to the firmware. This doesn't work out here, so we keep this for the next video where we dump the firmware directly from the chip. Back to this one. So in our case right now, we simply log in with the password. After logging in, we can now access the bootloader commands shown in the help menu here. We start our hacking process and therefore, yes, we have to switch the terminal color to green because otherwise no one will watch it on YouTube. If we print out the environment variables, we can see one interesting line, the bootcmd line. This line is reading the content from the flash at this offset with the size of these many bytes and stores it at this address in RAM. The RAM of the camera device is the same RAM as the bootloader running right now, so this terminal window. With sfprobe 0, we select our flash storage and the sfread command reads the content from the selected flash at this offset with this size and loads it into RAM. Let's verify this. Let's check the content of this RAM address right now. We use the memory display byte commands and here we have it. It is mostly uninitialized memory. This is now the RAM of the camera device. Now we select the flash with sfprobe. And now let's read the content from the flash into the RAM. We display the content of this RAM address and there we go. Linux kernel image, awesome. If we compare this to our drawing, we are here right now. The device would now normally execute the code at this memory address and the system will boot up. We do not want to start the system, we want to perform some more flash reads, so let's do some more. Here we have a dump of the flash chip, which is something for the next video, but let's use this information to verify a few things here. We make multiple dumps and calculate the MD5 sums to verify that our flash reads were successful, but more on this also in the next video. If we now use binwalk on this flash dump, we can see that the device tree blob starts at address 0x4 and a bunch of zeros. Interesting, right? You remember this value? Yes, let's open this file with imhex and let's jump to this address. And there we go. This is now the raw flash dump and the content at this offset is the same as we have in our RAM right now. Let's verify this and let's jump to the bootloader in our flash dump, which is at address 0xa310. Okay. Let's load this content into the RAM and display it back. And once again, we load the content at address 0x41 and a bunch of zeros. Now we display the content and there we go. This is now the content of the bootloader in our bootloader. I mean, we are just loading the content and not executing it, and therefore we are totally fine. Let's do some last flags. The Jefferson file system, also no problem. Here we can see the magic header and this is how binwalk recognizes the offset of this file system in the flash dump. It's all just about signatures and these are the magic bytes for the JFFS. Now let's load the whole content of this flash into RAM. We have enough space there because, let's think about this. We are having hundreds of megabytes, even gigabytes in our RAM, but just a few megabytes for our flash. In this case, 16 megabytes. We can get this info from the datasheet. Therefore, we take the same address in the RAM as before. We use the offset in the flash, which is 0, and a size of 16 megabytes, which is 0xFF and a bunch of other Fs. All we need to do to store this into a file is, yes, we simply activate the logging, we clear the screen, and we start this process. So this process might take up to 2 hours. The hex dump has finished and we therefore immediately stop the logging into the file. Now we need to parse the file. Let's print it out first. Okay, we can see we have a nice hex dump, but the address lines and the ASCII lines are not required. To extract the bytes out of this dump, we are using cut, and we play around with the amount of columns until we select all bytes in a row. We save this into a file and convert it with XXD into a binary format. If we perform now an MD5 sum, we can see they are not the same. Oof. The size is 1 byte off. Let's open both files with imhex and let's see what's going on. The diffing process itself does not show any differences, which is kinda interesting. If we go to the end of the file, we can see, there's one FF missing in one of these files. Let's simply add this 1 byte in our file, and now let's compare the MD5 sums again. And awesome, now they are the same. We have now extracted the whole firmware via the bootloader. So now we can extract the file system, the JFFS, and we can now start our vulnerability analysis of this device here. Perfect. In the next video, we take a look at how to dump the firmware directly from the SPI flash.